Okay, so we'll start today's lecture. So what three types of clustering, family of clustering techniques that we discussed last time? Partition, right? And what do we do in partition? Okay. Yeah, fine, but mainly you divide them into groups, right? Of normally what you call a spherical shape. If you remember, I was drawing like a circle, right? Like a sphere. Then we talked about the hierarchical levels, multi-level clustering. And then we started talking about density based, right? Which is somewhat partitioning method, but the shape can be arbitrary. Arbitrary means they can take any shape. I wanted to start off by giving some examples of because it's a big question, which technique would you be using if you have a particular scenario? So let's look at few cases, okay? And then you can kind of guess, what is the best technique here. So let's start with the first one, document classification. We have documents and we just wanted to categorize them. What do you think? Or is it looking like there could be even multiple? It depends on your objective, but just basic level separation of in a single level. What do you feel could be a technique we could use here? Hierarchical means multi-level, right? Yeah, I'm saying just basic level separation, first level. Partition, right? Yeah, you have to say a little louder. This glass prevents voice from coming. So please just when you say, please just say a little loud. Okay. So what about delivery store optimization? These days drones are being used to do deliveries. Maybe still not here, but in let's say North America, right? Companies have started, like Amazon has started to make those deliveries. Now you have to kind of group areas for selecting which drone goes to what area. So it's like you have to identify areas for which you have to assign drones. Again, what kind of problem do you think it looks like? It could be density, but here they are looking at, because normally drones, go in like, you'd like to draw a circle in which the drone goes, this side, that side, that side, that side. So they can be an argument for density based, but normally, people are using what we call k-mean clustering for this problem, right? Which is fine. You had certain argument in mind because you're looking at a geography, right? So there is no one correct answer to these problems. So you can always argue which one is better, but fine, at least you're looking at partitioning methods, okay? So identifying crime localities. Maybe density based, maybe k-mean, depending upon, because localities cannot be always in circle, spherical, right? So maybe density based clusterings are better. One of the things that is pretty obvious whenever you're dealing with, it's not very clear here, whenever you're dealing with what is called geospatial data. Geospatial data means data spread on Earth. Like houses, like locations and these things. Normally the best choice is always density based, because the shapes are really like spherical in the form of circle. So remember, anything when you're talking about, like, I think your guesses were pretty fine when you said about drones and crime localities, you're pointing to density based, because they are essentially what you call geo means Earth, right? Geospatial data means space on Earth. So geospatial data. Now, one example from hierarchical, which is very interesting, how different animals are related to each other. You can see that brown bear, polar bear, black bear, and then spectacled bear, giant panda, raccoon, and red panda. So complete relationship structure is here. So which two seems to be very, very close to each other? Which two seems to be the closest if you start reading this map? Because eventually the software will create a map for you and then you can explain. Now, we are going to talk about this mode, but first of all, when two of them are connected, it means that you're showing connection. And if the height is small, it means that they are very close. And if the height is tall, it means that even if they are close, there's still big differences, right? So which two of the animals you see as the closest when you compare all of them? The brown and the polar bear seems to be the closest. And then if you compare these two together, the next closest is the black bear. Which one is the most farthest one? The red panda. They call it the red panda. Even by looking at it, you can see it looks very different, these two, right? So even this one is making sense when you start looking at these pictures, right? Even if I don't show you, you'll still see, oh, these two look very different, right? And this is what it is saying. These two are close, but still big difference. But they are, look at the height between these two and the rest. They are very, very far apart. Okay, the height telling you how far or how different they are. Okay, so I mean, you can see, so the next one and the next one and so on. So in such applications where you want this multi-level comparison, then hierarchical becomes a very, very good choice. So I just wanted to show you some examples. So we will continue from where we left. So I'll very quickly go through what we did, but basically we have to start from density-based clustering. So we talked about, you already mentioned that we are talking about partitioning methods, hierarchical methods, and density-based methods. So these are the three big groups. And within the groups, you have more techniques. So we said that partitioning is about putting n objects into k partitions. So k partitions, so k is predetermined in partitioning methods. And you initially create, and inshallah today we'll look at it, we'll initially create partition and then improve and find the right clusters. And then I think we saw that, typically, although just for simple visualization that, how groups are iterated, this is the starting one and this is like the end one. So with the iteration, it keeps on improving itself and creates the best possible cluster. Again, you can see that it starts and keeps on improving. And today we'll learn this algorithm which is going to do something like this. A few iterations, it will improve itself. Then hierarchical, I already gave you example about those hierarchies, and the hierarchies are being created there. So we talked about that. Now I think this is where we started. Yeah, we stopped there. And we said that there's a big problem with not one, but multiple problems that inshallah later we talk about those problems more in detail. That K-means has certain restrictions, limitations, and problems which will not be very helpful in solving your problem. First of all, K-mean results in what you call spherical clusters. Spherical means somehow, if you see the group, you can draw kind of a circle around it. Circle or square, okay, maybe an oval. But they follow that circular kind of shape and spherical shape. Now, what if the data doesn't follow a spherical shape, like like in a geospatial data where you have like an arbitrary shape? Some very strange shapes can happen when you're looking at, like, let's say from a drone, localities and various things. Like think of Hajj movement. I gave you about this Hajj movement example. The crowd might be moving in a very not non-spherical way, right? But in so many arbitrary forms, you can see it from the top. So yeah, plus we'll see. Or let me keep that talking about outlier issues and so on for later. So in order to deal with such situations, we use what is called density-based methods. Distance-based clustering methods can only result in spherical shaped clusters. We already mentioned that. And encounter in finding clusters of arbitrary shape. I already explained that. So the density-based methods are based on the idea in which clusters continue to grow until density in the neighborhood becomes thin. So you start somewhere and you see a crowd, right? And you start watching, how this crowd is developing, and you keep on going until this density becomes less. So what is density from physics, from your high school? What is the formula for density? Remember? Anybody remember? I'm teaching you even physics and maths and everything. Mass over volume, which means what? The higher the mass in a given volume, the higher the density. So if you are carrying 1 kg versus in the same space, if you're carrying 2 kg, which one has higher density? 2 kg, right? Because it means that in the same space, you're fitting in more volume. Exactly the same concept is here. If you're fitting in more objects into a smaller space, then you're looking at a higher density. And we're trying to capture those high density zones, whatever you define as high density. Okay, so we are looking for high density ones, high density zones in our data. Everybody understand this concept of high density? Yeah, so we are looking at that, and somehow we try to keep on tracking the neighborhood. So if there's a crowd here, what I will do is I will start to walk around and see, okay, there are lots of people here, or it ends here. So I kind of travel in the crowd to kind of create that whole region, which has this high density. Okay, so conceptually we'll see algorithmically how it is done, but this neighborhood concept then becomes important because you keep on looking into the neighborhood. Okay, so clusters are dense regions in the data space separated by regions of low density. So you find high density, then you find low density. So you just identify high density as a cluster. Then low density, you keep on looking for the whole space. And then you again find a high density region and you identify that. So you identify all those high density regions. Again, we have not defined what do we mean by high density. Conceptually, we understand, but there has to be what you call, maybe on some other screen, you'll see there is a threshold. Threshold means 2 kg and above we call high density. That's what we call. Threshold is a number above which we say it's a high density. So someone has decided, the domain expert must decide that what is the threshold that we say, okay, below this density is low density and above this number is high density. So, something called a threshold value. So, and then, you may have those high density zones, and then, those that are not part of those high density clusters are normally regarded as outliers. And outliers cannot detect that. Partitioning method cannot detect that, because if you remember, one of the rules was each point must belong to one of the cluster. You remember that? Here there is no such rule. There is a rule. We are forced to put that point even if it's an outlier to a cluster. Okay, so here there's no such restriction. So the applications are completely different. So you're looking at an example here. This is, visually you can see it's like a high density zone, right? High density, but low density. But this is where it gets interesting. You see that you're just by visually looking at it, it seems maybe not, right? Maybe it would have been like outside the cluster or not, right? So this is what we need to understand, how the algorithm works. Conceptually, we'll learn today. Later, we'll see if we can do it. For sure, we'll do it on software, but mathematically, we may or may not do it. We'll see. But this is why we use clustering, because there is like an uncertain thing, similar, more similar, less similar, right? Low density, high density. So we cannot just do it by hand or manually looking at it. There's like a question mark here, right? So this is obvious, right? Why do we need an algorithm for that? But yeah, for why this is out and why this is in, this is where you need like an algorithm making the decisions for you. Okay. Let's just move on. So to understand density-based clustering, we need to understand few concepts. What is this symbol? Anybody know this symbol? Anybody know Greek alphabets? What are Greek alphabets? What's the first one? I'm sure you know about some of them. Alpha, beta, gamma, delta. So one of them is called, this is called epsilon. This is not E, but if you like to call it, it's fine. But this is written like this. This is epsilon. So epsilon neighborhood. Epsilon is used for any object. E neighborhood or epsilon neighborhood means E for a particular point that you're calling epsilon or E, you have to look into its neighborhood. So E is the object. Let me call it E for ease. Okay, it's not E, it's actually epsilon. But E means whenever you're standing on an object, that's the E that is under your scope. You know, like you always have a point on which you're having your own scope. So that point is E or epsilon. Okay, and then there's something called the neighborhood, and the neighborhood is exactly what you understand. You know, you live in a neighborhood, right? So it's the area around your house, right? That's the neighborhood. So objects within a radius of epsilon from an object. So if this is a point, what we'll do is we'll draw a radius of size epsilon, we'll draw a circle. That becomes the radius for that, E neighborhood for that, epsilon. And who's standing here? What is this point? That's the object, right? For which you're finding the neighborhood, okay? That's the object for which you're finding the neighborhood. Okay, so everybody understand what's E neighborhood or epsilon neighborhood? It's the object's neighborhood which you are able to find by drawing a circle of radius this. Okay. Again, you should ask, where are you getting this value of E? You need to talk to domain experts, and they say, this makes sense. This number is making sense for defining this. This should constitute a neighborhood, right? So it depends on the problem. It depends on the context. You need to learn with the subject matter experts, and they can tell you that this should be a reasonable size for a neighborhood. Okay, so let me give you a few examples which will make your mind more clear. If you're talking about your homes, or simple homes, what should be a typical neighborhood? How far do you consider to be still neighbor? Maybe like 200 meters, 300 meters, 500 meters, right? Maybe a kilometer, right? But when you're looking at survey map, looking at like cities, what should be like the neighborhood you would call a neighborhood? Maybe 100 kilometers, right? Yeah, something like this, right? At least we are arguing for it, right? That's how you argue. That's how you come to a consensus. Maybe you'll say not 100, maybe 50, maybe somebody would say 200. Fine. Let's sit and discuss and decide. That's how you decide the number. That's the point. So high density zone is in this neighborhood of an object which is residing here at the center. If this neighborhood contains at least some number of points, again you decide. Again, this is the same discussion. You say at least 3. If you find at least 3 more objects within this neighborhood, then you call this what? High density region, high density neighborhood. Okay. So this epsilon and min points are what you call input parameters that you have to decide before running the algorithm. Again, you know where these parameters are coming from, right? These parameters are coming from the domain experts. So if you understand these concepts, then we can classify these points that we are evaluating either to be what you call a core point, a border point, or a noise point. So a point, by putting a circle on top of it and looking into the neighborhood, we can decide whether this point is a core point, a border point, or a noise point. So let's look at an example, and then you'll be able to understand this better. So what is epsilon? Yes. Epsilon here is, you can see from at the top, the data, the input parameter values are already given to you. Epsilon is 2 centimeters, and the minimum points in this neighborhood to call it high density is 3. So what you do is, let me try to use this thing. So let's take this point as an example, right? So I'm going to draw so that you can clearly see the circle around it. Am I drawing it correctly? Ah, bad choice. Oh, I thought that this is like. Let me use this one. Let me draw. Let's not make this up. Let me draw it here, okay? Okay. So I'm going to draw a circle around this point. Okay. Let's start with something more, something that we wanted to talk about. So how many points do you see around the neighborhood? Around its neighborhood, within its neighborhood? 3. So is it, if you find the minimum points, you call it a core point. So we are calling this point a core point. Now I'm going to start doing this for all the circles. Okay. Let me draw a circle around this point. Oh, sorry, my bad. Wrong circle. So how many points are there around this particular point? 3. So still a core point. Now, do you see here that we keep on building these circles, and these circles are overlapping each other. So they are creating a region for you. A lot of spheres combining each other and creating a region. This region is separate, this region is a separate thing. Now it can form any shape you like. Now we do understand core points, but let's draw this thing, a circle for this one. Does it have 3 points in its neighborhood? This circle, 2. So it's not a core point, but it is connected to the neighborhood of a core point. So what do you call that thing? Yeah, let's see the definition here. A border point has fewer than midpoints within its neighborhood, but it is in the neighborhood of a core point. So you still connect to it. It's the neighborhood, right? So this is so this point is still connected, but we are calling it in the neighborhood. Now, if both the conditions are not met, a noise point is any point that is not a core point nor a border point. So let me just draw a circle here for this one. Does it have enough points in its neighborhood? No. Is it connecting to the neighborhood of another point which is a core point? So it's a noise, right? So you keep it separate. So this is like a noise. So maybe this is like a border point. Maybe this is like, because if you draw this circle, it has like 2. Maybe for this one it has 3, right? So that's how the algorithm creates those shapes for you, and that's how you create density regions. So this was the original data. You can see that the green ones are like the core points, the blue ones are like the border points. You can see that they are at the border. So they themselves do not have enough points, but they are in the their neighborhoods are overlapping the core points, right? So if you draw a circle here, it's a core point, right? So it's touching, it's overlapping, but not this one. So these are what you call the noise points. So I hope you understand these the 3 concepts: the core, the border point, and the noise. So this is just a high level description. I think it's time that we are ready, and we'd like to we'd like to jump into real business. So we actually wanted to do an algorithm, run and find the solutions. So we'll start. Okay, so we are going to start this k-means clustering. So which family does it belong to? I mentioned that to you. Partitioning method. So you know what partitioning does, right? It creates groups, segmentations, right? And then we'll talk more about k-means. So our discussion will stay on k-means only. Okay, so we'll talk about k-means and its limitations. So this is us. The algorithm is very simple. You can do it by hand. The only problem with doing it by hand is that when the data becomes large, then it becomes very difficult to manage. You can even program it, but I'll not ask you to program it. The good part is there are already software out there which can do k-means clustering for you. Very, very nice software. And I mentioned about that, inshallah. Maybe I'll ask you to bring laptops with Orange installed next time. I'll see. So how does it work? I think you should be able to understand all these lines now with your concepts already well made about some of those things. So compute distance from all points to all k centers. Is it understandable? You know what does distance mean? Distance between 2 points. Yes or no? How do you measure distance between 2 points? Name the formula that we use. Yeah, Euclidean, or we talked about Manhattan distance, right? You remember x minus x square, y minus y square, z minus z square, and the square root. So that's how you're going to find the distance between all the points in your data with. So it means there are k centers. What are k centers? We use another term for it. Anybody remember the term used for k centers? Centroid. So this is just another name for centroid. So these are centroids. So it means what? So we have a data set and we have k centers given to us. I'm going to again talk about that. You remember chicken and egg and chicken, not chicken. Egg and hen, I don't know. Hen and egg, you understand. I'm losing my track here. So that discussion which comes first, so that we have to discuss here. Inshallah, we'll talk about that. But given that we know what k is, we have to find the distance. Assign each point to the nearest k center. We already discussed that. You remember last couple of classes? We said that whichever is closest, you assign to that. It's exactly saying the same thing. Now compute the average of all points assigned to a specific k center. Find the average, which basically is telling you to find a new center for it. Now, so so for example, if these were the points, and you have created like this, and you chose this to be the center, and you assigned. Now these are the points you'll see that the center might change. Because you take the average of all x, the error of all y, the average of all z, and whatever, right? We'll see an example and it will be more clear to you. But this will give you, replace the k center with the new averages. So that becomes the new center. And then you keep on iterating it. Iteration, it's the same term from Python, right? The for loop, I used to say that you need to iterate, right? Iterate means like go into loop. You keep on doing it until the k centers stop changing. So if in the next loop, the k center, you find a new center, you do it again. In the next loop, the iteration, you find a new center, you keep on doing, but in the next one, there was no change. They are the old k centers, there is no change. So it means that you have found the k centers you were looking for and you have found the right cluster. Yes. No. Let's look at an example. Not each point. I say, you find an updated point which will improve your actual natural center to that cluster. And now because you have changed your center, it means that you will delete the boundaries again And you'll say, okay, I found these two new centers, let me repeat and reassign points to these new centers, right? And then from the new grouping, you again try find the center. If the center changes, it means that you still haven't found the right one. And then maybe center shifts here. So the center keeps on moving until you reach the natural one. And then, even if you repeat 100 times, nothing will change. Right? So let's look at an example, and it will make things much more clear here. Okay. Let me see if there is anything important here. So the K must be known. We already know about that. Now the egg and the chicken issue. So this is the solution. The initial step is to randomly choose, the number of points. Which, for example, if you're saying K is 2, so from your data, just randomly pick 2 points as center. Randomly. There's no rule. It's as simple. Randomly pick that. Okay, my K is 2, these 2 points are my centers. That's how you start. Okay, which means what? Every time I start K means I can pick a new center. It doesn't matter. Eventually, you'll reach to the same point. You run the algorithm 100 times, you'll still reach to the natural center. The method I told you. So it does not matter where you start. The only difference might be that if the pick centers are very odd, the iteration might take a little more. Maybe if you're finishing in 5 iterations, maybe far away, very far away from the natural center, if you pick those points, maybe instead of 5 iterations, you'll be needing like 8 iterations, 10 iterations, whatever, right? So it takes a little more while or less, but the end result is the same. So next, the algorithm considers each instance data point, and I think the rest we have already explained. So let's look at this simple example. So how many attributes we have in this data set? You see a database DDA. Yes. Sorry. Okay. So attributes are where, in columns or rows? 2 attributes. And how many data points you have? 6. So you're talking about 6 points. Okay. So let's do something which will help us. Okay. I think I need to throw this back. Yes, we can use that, and this is what I'm trying to do. Because it's ease of visualization, it's only 6 points. Okay, I'll try to make it. Let's try to plot it. Normally we don't plot it because we have thousands of points, right? We cannot plot. Plus the attributes can be more than 2, 3, 4, 5, 6, right? But let's just draw what is we'll say 1, 2, 3, 4, 5, 6. Let's draw 6 by 6. 1, 2, 3, 4, 5, 6. So what is the first point? 1.5. This is, I'm going to call it point 1. The point 2 is 1. So 1, 2, 3, 4.5, right? This is point 2. Make sure I'm not making any mistake. Okay, the third point is 2. So this is point 3. Point 4 is 2. 1, 2, somewhere here, right? Okay, that's number 4. Then 5 is 1. I should write 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So 3 and 2.5. So this is 0.5, right? And then we have 5 and 6. This is point number 6, right? So can you see visually? Can you see how many clusters would you suggest? Somebody said 1, 3, 2. How many of you think that there is one cluster? I heard one voice, so there's a change of mind, right? How many thinks two? So let's count. Tell me how many. Raise hand and tell me, is it a? We'll go with the majority decision. Look, just look visually. Look, this one seems far, right? No, partitioning. There is no outlier. Yeah, right. You have to understand partitioning method. We are not considering outlier. We're not into detecting outliers. Okay. Do you think these seems like in neighborhood of each other, close to each other? So maybe if I draw, I would be looking at maybe something like this. I don't know. I'm just visually this is my hunch, right? So maybe we'll take care to be two, right? Or my domain expert, even not looking at the graph at all, my domain expert told me that the data can be expected to be divided into 2 or 3 groups. Okay, so we'll start doing it with 2 groups. So now we have to do what? What was the first step? What was the first step? Yeah, so I randomly choose 0.13 every time because my lecture has. But I mean, randomly means like you can pick any of the 2. Okay, so it could be 1, 6, 6, 5, 4, 3, whatever, it doesn't matter. So assume that we have picked 1 and 3 as random points. So we are calling this C1 center for cluster 1, and this is center for cluster 2. Now, what was the second step in our algorithm? Which means what? We have to find distance of all these points from 1 and then all these points from 3. Of course, 1 with 3 is meaningless because we know that we have assigned them as 2 different centers. Okay, so let's see if we can do that. So distance from C1 to 1, C1 is 1. So distance by itself, that's what you're looking at, right? So that's why C1 with 1 turns out to be 0. What is more important is the other one, 1 with 2. Who can you help me find distance with 1 and 2? Let's try to maybe do it here. We would like to use what? Euclidean distance or Manhattan? We'll be using Euclidean distance. So what should I write here? What is the x for 1? What is the x for 2? 1. I have to do square, right? Plus what is the y for 1? Okay. So this is 0 and this is what? So can you 3 square is 9, 9 square root is 3, right? See if we have the same answer here. Not very difficult, right? That's how you compute the distances. The only problem you see here is you have to compute a lot of distances. So when it comes to understanding the problem, we are just limiting ourselves to 6 points, right? So a lot of calculator use you have to do. Even in exam, it will be fewer points, but certainly not in practical problems. You can never get it done by hand because there are too many computations to do. But let's just keep on looking at it. This is computed, but I'll draw kind of a line here because we know that 1 and 3 are 3 is already be defined as a center. Where's my point? Oh yeah, here 3. So let's try to do one more. Let's pick an odd one here. Okay. So or maybe this one. 2 with what is center 2 with 5? Center 2 is what point? This is center 2, right? And with 5. That's what we are doing. Can you use your calculators or to find me? What is the answer for that? So it will be what? 2 minus 3, which square, which is 1, and then 1.5 minus 2.5, which is 1. So 1 plus 1, 2. 2 square root of 2 is 1.41. That's what you're looking at, right? So you compute all the distances. Now comes the next step. Now, once we have all the distances, all we have to do is very simple. See 0.1 by itself, of course, that is contained in the first cluster. Let's see which one is smaller distance. 2, is it close to C1 or 2, is it close to C2? So we put it here. What about 0.3? Is it close to C1 or is it close to it point by itself, right? What about 4? 4 close to C1 or 4 close to C2? So we put it in C2. What about this one? Look, 2.24 and 1.41. C2, right? What about this one? 6.02 and 5.41? We put it here. We created a cluster. So the next step, what was the next step? Anybody remember the next step? To change the center, you have to find the new center. How do you find the new center? You average. Average. Okay, how do you find the average? The first cluster contains 0.1. What were the 2 points it was containing? 1 and 2, right? 1 and 2 and 3, 4, 5, 6. We intentionally created a problem that's easy to follow. Okay. So 1 and 2. So 0.1 and 2. So you have to do 1 plus 1. You can see up there. 1 plus 1 divided by 2. And then 1.5 plus 4.5 divided by 2. So what is the new center? 1, 3. This 1, 3 is now a new center that we have found. And what about C2? C2 is like 3, 4, 5, 6. So 2 plus 2 plus 3 plus 5 divided with how many points we have? 4. So we divided it with 4. So it turned out to be 3. And then the y, find the average. So 3, 3.75. So you can see that the previous coordinates, this was C1 before. This was C1 and this was C2. So the point new C1 is 1, 3 and new C2 is 3, 3.75. Are these the same or they are different? C1 is 1, 3. What was the original C? Is it the same or is it different? What about this one? Major difference, right? 1, 4.5 here, 3, 3.75. So it means that you have a new center. Now you just repeat exactly the same process what you have done. You find the distance with C1 with all the points and then reassign. You compute the new centers. If this center changes, you repeat again. But maybe third time or whatever, if this center doesn't change, next time you take the average and it stays the same, you have found your clusters. As you can see that it's computationally, it's not very difficult, but computationally hard. You all agree? Computationally hard means what? Too many calculations, right? Agree or not agree? But is it difficult to understand? That you have just learned k-mean clustering. You already know now one partitioning method. What is that method? K-means, not mean k-means clustering, okay? So we'll inshallah try to solve more problems in the class, but here are a few things you need to keep in mind. What if my data contains 3 attributes? One says age, the other says height, and the fourth says gender. You see the problem here. How can we say age minus age and gender? How can I subtract F and all those, right? So the k-means algorithm works only with real numbers, which means numbers with fractions and so on. If you have categorical attributes, categories, categorical means like male, female, or whatever anything which you can put in categories, then we'll learn later how to deal with it, towards the end when we talk about different clustering techniques. But just to give you a very small hint, you can a crude ways just to convert them into numerical equivalents. I'll call, for example, one the female and like 0 male or whatever. So can convert them into numbers like this. But the discussion is not over. We right now will focus on just the algorithm itself, but I can throw you some issues to talk about. So what if one attribute is more important than the other? Right? Do you see? Do you understand what I'm saying? What if one attribute has big numbers and start to dominate the algorithm, forcing clusters to be found around that attributes and ignoring the other attributes because those numbers are big. One numbers are in hundreds, the other numbers are in like ones and twos, or even fractions, decimals. So those numbers which are in hundreds will start to dominate. You can see if these numbers are in fractions and these numbers are in hundreds or thousands or 10,000, which term will dominate? The bigger ones, right? So we'll inshallah talk about those things in detail. Right now, you just need to know the steps. Steps means start with the data, arbitrarily identify your points from the data itself. K is given to you, and then you repeat all the steps, and then you'll be able to reach to clusters. Okay. And the example we talked about colored values. Again, you can arbitrarily assign like 1, 2, 3, 4, 5 different values to different colors. Number of clusters to be formed is predetermined. So we know that we started with K2. We just had a discussion whether 3 makes more sense. Some of you are saying maybe 3, right? So that's one of the problems I showed you. Like, how are we picking this K? This picking of K is a problem. It's predetermined and may result in poor clustering because our choice was not good. Right? So we picked 2, perhaps 3 was the right choice. So what do you do in that case? You have to try out various Ks, and the domain expert need to interpret the data. We have so far haven't looked at the real data where the domain expert can actually see, it makes sense. That's what my hunch was telling me, right? So this is another consideration for k-means. Very sensitive to outlier. Start to behave badly when you have something like this. Now, I'll give you an example here. Okay. Well, what are the 2 rules that you must have in k-means? And I'm assuming K to be 2, which means that how many clusters I need to form? 2. Do you think it makes sense because I need to fit 2 clusters to find 2 clusters from this point, this shape? Where do you think my center would be? This center is getting affected by how many points? One real big bad outlier can affect even the center of your cluster. Just look at this visually. So you have to take average, right? Ideally, it should be here if you just look at these points. But because of this, it's a big number. This center might be dragged, and this center even is not the best representation of the whole cluster. So outliers are bad when it comes to k-means. Of course, we know that we have other algorithms to deal with it. And even if we have to do simple partitions like this with outliers, we'll look at another method called k-medoids that specifically address this problem. Okay. So any question? So there's no way to tell which attributes are significant in determining the found cluster. I already mentioned that, which attributes are more important or less important, or if I want one attribute to be more important, then how to deal with it? We'll look at that after a few weeks, 3, 4, 5 weeks. Okay, so a lack of explanation about the nature formed. So these clusters are formed. We need to explain. Who can explain why this cluster exists? What is the meaning of this cluster? The labeling issue that we talked about. So again, whose job is that? The domain expert. They can see and they can explain why this cluster is formed. What does this cluster mean in our data? Okay, I think I'll stop here because I want you to solve this problem in class by end next time. Okay, so next time I'll give a message. Let's just wait. I'll see if we have time. Let me plan the next lecture. Otherwise, I'll send you Excel files with real data. Not 6 points, but 600 points, 6,000 points. And then I'll ask you to do, and maybe 2 attributes, maybe 5 attributes, right? Different sets of attributes. And I want you to run. Can you see those clusters being formed? Yes. So we'll see, and then we'll try to see if we can interpret those results a little. Maybe we'll not be able to, without domain experts, we may not be able to fully understand, but we'll see if we can interpret those results. Okay, any questions? You're all clear. Everything is clear. You don't ask a lot of questions, so I'm hoping that you're following. Okay. So you want to leave home early, or you still want to have some discussion? Okay. So inshallah we'll meet next week. Thank you. Take care, everyone. Let me stop the recording.